Hey guys, hope you're doing well. Welcome back to the calculus channel. Wait, did I say welcome back? Nobody watched the video I put yesterday. So I don't know if I'm welcoming you back at all or not. Can't believe that there were more Bridges students that watched the video I posted than there are calculus students. Ay, ay, ay. What is the world coming to? Okay, anyway, so today we're going to continue talking about finding volumes of solids of revolution. But this time what we're going to do, excuse me, is we're going to rotate them around the y-axis. So that is going to be super fun. All right, so let's get a little sketch of the graph that we're dealing with to start. So I got y equals x cubed, so that's going to be this, and then there's a left-hand part also, which we're actually going to skip. Then it is y equals 8, and x equals 0, and so x equals 0 is the y-axis, and so that defines this little region right here that now we are going to spin around the y-axis this way. So the good news is nothing really changes except that everything changes. And what I mean by that is yesterday we were integrating with respect to x. Now everything is just going to switch around and change so that we're integrating with respect to y. So we still are looking for the area of the cross sections, but this time we're in the y direction because we rotated things, and that's still going to be defined by donde está mi pi symbol. I'm just gonna, oh, seriously, it's under Greek, I guess, huh? Okay, I'm just gonna, maybe I'm not. That's going to be pi times the radius squared, because we're still dealing with cylinders. The difference is this time the radius, since we're going, like I said, this way, the radius is going to be defined by the x-coordinate instead of the y-coordinate. So it's going to work out to be pi times x squared. Okay, so to get that going, then the first thing you notice is that the equation that they gave us is y equals, so I have to solve that for x. So hopefully it's clear that if y equals x cubed, x equals the cube root of y, which in this case I'm going to write as y to the 1/3. So then that means the area of my cross section is going to be, why am I using a y here, I wonder? I guess because y is our independent variable. The area of our cross section is going to actually be pi times y to the 1/3 quantity squared, which we can simplify to be pi times y to the 2/3 power. And it's as simple as that. So now we need to take and figure out the integral. Do you think we have an integral symbol in here? Oh, I thought that was it. No, that's a function symbol. Alright, so I'm going to just draw that by hand. It's not going to be pretty, so I have to do the integral from, we're going from here to here, so from 0 to 8 of pi y to the 2/3 dy. Now remember the pi is just a constant, so I'm going to pull that out in the front, and then go y to the 2/3, and then dy, again this time because if you think about the cylinders, what the dy, again, talked about this yesterday, really represents is it represents the height of each one of these infinitely small cylinders. And so that height right there, since it's in the y direction, it's got to be dy instead of a dx. Okay, so pi times the antiderivative of y to the 2/3 is 3/5 that's a parentheses, BT dubs, and that's a 3, by the way. 3/5 y to the 5/3. And that's convenient because we all know the cube root of 8, so we can do this without using a calculator. Let's do an 8 that way for the first time in our lives. It's an ever-changing landscape out there, I tell ya. Okay, so we're going to go 3/5 times. If I plug 8 into there, I'll just write that out. So that's 8 to the 5/3. Okay, so the cube root of 8 is 2. 2 to the 5th is 32. So this is pi times 3/5 times 32, which in the end is 96 pi over 5. Okay, that's it. Strange but true. That's all I'm going to throw at you today. Again, nobody watched the stinking videos from yesterday, so who knows if any of you will ever end up doing this in the end after all. So here are some problems for you to try related to this. I will work through those problems in the next video. Now, you know what? Let's just keep going here. So there's the problems. There's the assignment. Let's just keep going. All right. So I don't have that open. So let's open up section 6.2 problemas. All right. So, okay, so let's take a look. So, first thing we got to do is draw a graph. And once again, white does not help. Okay, x equals 2 square root of y. How the heck are we going to graph that? Well, let's think of what that would look like if we solved it for y. If I divided by 2 and then squared both sides. Okay, if I divide both sides by 2 and then square, then another way I could get this is y equals x squared over 4. So those are the same things. So x squared over 4 looks like a really fat parabola, because it's like 1/4 x squared, with its vertex at the origin and opening up. So that's this guy right here. X equals 0 is the y-axis, and y equals 9 is right there. So we're going to take this thingy and rotate it around. Now you might be wondering, the conversation we would have if we were doing this live, how do I know it's this side and not that side? The answer is, doesn't matter. They're both symmetrical, so if I take either one and rotate it around the y-axis, I'm going to get the same, solid of revolution. So that doesn't matter. All right? Okay, so let's find the formula for the area of our cross-section. And again, we're doing this in the y direction, so that will still be, seriously? Oh, because I was looking for the integral. So there'll still be pi times the radius squared, because for now anyway, we are just doing cylinders. Anyway, pi equals r squared. In this case, the radius is, again, we're going side to side, so the radius is going to be the distance from the y-axis to the graph in the side-to-side direction, so that means it's going to be pi times x squared. And they gave us the function for x this time. We don't have to solve it, so that is going to be pi times, I'm just going to square it, pi times 4y. Okay? So those are our cross sections. So that's fun, because now not only can I pull the pi out to the front, I can pull the 4 out to the front also. then I'm integrating from 0 to 9, because everything is sideways. And I'm doing y, antiderivative of plain old y. And say, where'd my music go? 1 half y squared. And again, I'm going from 0 to 9. So 4 pi times 1 half is 2 pi. And then when I plug in 9, that's 81. I guess I gotta type this. And then that equals 162 pi. Okay? So that's how number 5 looks. Fix my music and I will be right back. Okay, so let's try another one. X equals y minus y squared. So what does that look like? Well, that's going to be tricky to solve for y to see what that graph looks like. So what I'm going to do is I'm going to switch everything. So I'm going to change this into y equals x minus x squared. I'm going to change this to y equals 0. And I'm going to change to be about the x-axis. Okay? Alright, so I know that this is a parabola that opens downward. And then if I factor out the x, then that'll tell me where it crosses the x-axis. Crosses at 0 and at 1, so here and here. I don't really know where the vertex is, but I don't think I really care because I know it's going to go like that. I know that now I have y equals 0, and I'm going to take this and rotate it around the x-axis, so I'm going to make kind of a funky little football shape. This is where Shelby would say, wait, you can just do that? And I would answer yes. Okay, so now we're back to yesterday's situation where I am doing cross-sectional areas in terms of x, because I'm going side to side instead of up and down. Not to get too redundant, but that is once again going to be pi r squared. In this case, the radius is up and down, so that means that it's going to be pi times y squared. And since our equation we figured out is y equals x minus x squared, we have to figure out what pi times x minus x squared is. So let's do that. Whoops. So this is going to be pi times x squared minus 2x cubed plus x to the 4th. This thing squared, these two things multiplied together, then doubled, and then this thing squared. Okay, so that means that our integral sets up to be, I'm going to go from 0 to 1. I'm going to have the pi in front. And what I'm integrating is x squared minus 2x cubed plus x to the 4th dx. So that equals, give myself lots of room here today, pi times antiderivative of x cubed is 1/3 x to the 3rd minus the antiderivative of 2x cubed is conveniently just plain old x to the 3rd. Oh, no, it's not. Dang it. Sorry, that's going to be 1/2 x to the fourth, right? And then plus, I should make mistakes on purpose, like I usually do, and give you guys points for finding them. Okay, so that's our antiderivative, I think. Let me just check that real quick. Yeah, okay. And then we are doing this from 0 to 1, loving the zeros. So if I plug that in, then I get pi times, if I plug 1 into there, I get 1/3. If I plug 1 into there, I get 1/2. And if I plug 1 into there, I get 1/5. And so what is 1/3 minus 1/2 plus 1/5? Well, I feel like common denominator is going to be 30, really? Okay, so that's 10 over 30. Just do some quick side stuff here. 15 over 30, 6 over 30. Oh, so that's going to be 1/30th. So that's going to work out to be pi divided by 3. Yay! Alright, 2 down, trace mouse to go. Okay, y equals x cubed, y equals x, and then this time we're back to the x-axis. Oh, glassy eyeballs. Okay, y equals x cubed. So we did this basically in the example. Oh, no, we're not ready for this yet, because what this has got going is y equals x cubed goes like this, and then y equals x goes like that. And so we have this funny little region here where we have to do some subtraction. We're not ready to deal with that yet. So we'll come back to that one. In fact, we might be denso for the day, yeah, because all of these have 2 separate curves. All right, so we're going to call it. I know that's not very much calculus, so that makes everyone sad. But on Monday, when we come back, we'll have a longer discussion about how to rotate around curves that are not one of the axes. Okay, have a great weekend. Hope you all are doing well. Let me know if you want me to do anything different.